Hello everyone, welcome to my channel. Today we are going to discuss about electromagnetism. So here itself the electro means which is divided into two. One is which belongs to the electricity and another one is which belongs to magnetism, that is about the magnets. So first, before a 19th century, everyone thought that electricity and magnetism were two different concepts. They were not related to each other, that they were thinking before the 19th century. And in the 19th century, a scientist came and proved that there is a relationship between electricity and magnetism, and that leads to the chapter electromagnetism. And that scientist name Hans Christian Ørsted. So he was the first scientist who came to prove that there is a relation between electricity and magnetism. Now, how did he came to know that there is a relation between electricity and magnetism? So what was, at a very fine evening, he came and sat in front of his studying table, and he just kept out a compass. He had just kept a compass and kept near to his table. And in front of the table he has a table lamp, and he switched on the table lamp and he was doing some work. So after few minutes he observed that there was a voltage fluctuations. As the bulb was glowing dim and bright, there was a voltage fluctuations, and due to that voltage fluctuations he observed that there was a changing of the magnetic compass, that is the needle was being deflecting. As the voltage fluctuations occurs, the needle which is present inside the magnetic compass has become to fluctuate. He came to know that there is a relation between this, the magnet which is present inside this, and the electricity. And later on he had proved it with an experiment called Ørsted experiment. So Ørsted experiment, what he have done is he has taken two V sticks and he has taken electric wire and he has attached it to the battery. He attached it to the battery to the key. Now here the current passes from the positive terminal to the negative terminal. When the current passes from positive to negative, he kept a magnetic compass under the wire. So under the wire, like example, assume this as a wire. So as he had kept it over here, and below that he had kept the magnetic compass. So when the current passes into the wire, it produces a magnetic field around it and shows the deflections in the magnetic compass. This experiment leads to the birth of electromagnetism. So before going to this main chapter, let us discuss about magnetism proper. What is a magnetism and what is a magnet? So this is about the Ørsted experiment. So when current passes into the wire, it produces a magnetic field. Due to that magnetic field, the magnetic compass gets deflect, and again when you off it, it comes to its normal position, that is the north-south direction. But when the current passes through it, it produces a magnetic field around it, and that magnetic field is invisible to us. Now let's move on to what is a magnet. As we are learning from lower class, a magnet, like whenever we talk about a bar magnet which consists of a north and south pole. So a bar magnet is a substance which attracts the magnetic substance or magnetic materials like iron, cobalt, nickel. So here in a magnet we have two poles, which is one is the north pole and another one is the south pole. Now again, if you cut these two, again it becomes two individual magnets which occurs like this. Again if you cut it two, and again if you go on keeping on continuing it half, it becomes into two individual magnets. Now let's see the magnetic field and magnetic lines around a magnet. So North Pole, South Pole. Now the very interesting thing is to draw a magnetic field, the same compass which we have it here, with the help of a compass, as if you see, if you do the experiment practically, you will see that the magnetic field lines which are moving from north direction to south direction. The same here also, from north direction to south direction. So these are the magnetic field lines. So these magnetic field lines are starting from the North Pole and ending to the South Pole. So starting from North Pole, ending to the South Pole. So the magnetic field lines always starts from the North Pole and ends to the South Pole. Now, if you observe the picture over here, these magnetic field lines are covered with a certain area, like this area or field. We should not say it as area, we should say it as a field. Why? Because the magnetic field lines are three-dimensionals. So which occurs in the left, right, upside and also downward, upward and downward. Like here from this, if you see upward, sidewise, and also from downward also you can see. Now the field where these magnetic lines are being covered is said to be called as magnetic field. I'll show you one interesting thing. Now suppose if I take a small pin, an iron pin, which attracts to the magnet. Now as this is outside of the field, the iron nail cannot be attracted to the bar magnet. Now what happens if I bring it near to this? Now suppose if I bring it inside to the field, now what happens? Yes, it's get attracted. But if I bring it again closer to this, near to the poles, now what happen? Yes, it also gets attracted. Now what is the difference between these 3 points? Point A, point B and point C. Now if you see here, point A is outside of the magnetic field, so it doesn't attract. Coming to the point B, as it is inside the magnetic field, it will be attracted to the bar magnet, but when compared to the point C, as it is near to the magnet, it attracts stronger, and when compared to the point B, the nail which is present at the point B, it will be attracted but weaker. So this is about the magnetic field, and these lines are called as the magnetic lines. So this is about the general introduction about the magnet and magnetism. So magnetism is the property which attracts the magnetic material and repels with another magnet is said to be called as magnetism. Now if you observe here, so in north and south, as these two gets attracted, and the same north and south, here south and south, that is we have two same poles over here. As there are two same poles, these two magnet will be repelled out. So that is the property of a magnet. So it is a property of a magnet where it attracts the magnetic material and it repels with the another magnet which are having the like poles or same poles. Now that property is said to be called as magnetism. Now this electricity and this magnetism are bothly combined when a current is passing into the wire. When current passes into the wire, it produces a magnetic field. So that comes to the electromagnetism. Next, coming to the magnetic flux. Magnetic flux. So flux is denoted with the letter phi, which is a Greek word. Now what is a magnetic flux? So magnetic flux is nothing but the lines which are passing through an area. So that lines are, as we are discussing about the magnetism, that is a magnet, so we call it as the magnetic lines. So these are the magnetic lines. As these are parallel to each other, we call it as a uniform magnetic lines. And these lines are passing through a certain area. We assume it as some certain area like this, some area, it is passing through an area, that is said to be called as magnetic flux. So magnetic flux, what simple we can say is the lines passing through a area is said to be called as magnetic flux. If we say in terms of electricity, like as we have magnetic lines we have electric lines, as we have magnetic field we have electric field, and as we have magnetic flux we have, yes, electric flux. So here for magnetic field we need a north pole and a south pole, but for an electric field we need either a positive charge or a negative charge. That means a single positive charge is enough to create a magnetic field, or a single negative charge is enough to create a magnetic field. But to create a magnetic field, definitely we need a north pole and a south pole. So that is why magnets are said to be called as dipole. These are said to be called as dipole. And electric field, as we have positive charges and negative charges which are individual, these are called as monopole. That means they exist in a single. But magnetic, these north pole and south pole, they cannot be exist in individual. That means we don't have a single north pole, we don't have a single south pole. If there is a north, then definitely there is a south, which is said to be called as dipole. Now coming to back to the chapter concept. So these lines which are passing through a certain area which is said to be called as magnetic flux, which is called phi, and it is measured with Weber. So the units of magnetic flux is Weber. Next, coming to the magnetic flux density. Magnetic flux density. As you have learned density in your previous classes, that density is nothing but a certain mass which is covered with a certain volume. A certain mass which is covered with a certain volume. For example, I have a cap over here, which is an empty cap. Now assume this is having certain volume. Now if I filled this completely with a certain material or a mass, then it becomes heavier, then we call it as denser. If there is an empty, as this is empty, this is called less denser. The same way as a certain volume which is completely filled with a mass, that is said to be called as density. So here in terms of magnetic flux density is nothing but the magnetic flux which is passing through a unit area. Here in density we call it as volume, but now here in magnetic flux density we call it as area. That is what we can simply say is the maximum number of magnetic lines passing through a unit area which is perpendicular. Suppose these are the magnetic lines. So these magnetic lines are passing through a certain area. Assume this is a circle and it is passing through it like this inside. Now these magnetic lines are passing through it. Now can you tell me how many lines are passing through that area? Yes, 3. So 1, 2, 3. As 3 lines are passing, so we can give a magnitude of magnetic flux density is 3. Magnetic flux density is 3. For example, if it is passing 2, then we call it as 2. If it is having no lines passing through it, then we call it as 0 flux density. Now how can we derive a formula for this? Simple. The magnetic flux density is denoted with the letter B. So B is equals to the magnetic flux phi by passing through an area A. So that is B is equals to phi by A. Now from this we can derive another formula which is phi is equals to B A. So magnetic flux is equals to magnetic flux density into area A. Now in this way we have a SI unit which is called the flux. Just now as we have discussed, it is Weber per. A is for area, which can be written as meter square. So overall Weber per meter square is SI unit for magnetic flux density, or it is also called as Tesla. It is also called as Tesla. So 1 Tesla is equals to 1 Weber per meter square. The very most important thing which may ask in a competitive exams or in your 10th grade examinations. Now here if we see the number of lines are passing through this is 3. Now what happens if there is no magnetic flux, that means no magnetic lines are passing through that area, then there will be no attraction. As if you see in the case A, here the magnetic flux density is 0. That is why there is no attraction over here. When you compare to the point B, there is a magnetic flux density, but as it is inside the field, it may have a certain, if you take a certain area, so one line is passing through it, so we can take it as 1. But over here at the same area what we have taken here, if you take it, so here we have 3. Now tell me, here the magnetic field density is less, that is we are having assuming it as 1 value, and here the magnetic field density value is 3. Now where will be the strong attraction? Yes, at point C, as it is having the magnetic flux density as 3. As there is more flux density over there, that means the attraction also will be more, and here the flux density is less, so the attraction also will be less. Now if we go into a little bit depth, so here phi is equals to BA cos theta, but if the area has been tilted to a certain angle like this, if it has been tilted to a certain angle, see just now it was 3, but the same area if you take it here, now it is 2, that means it has been decreased. So if it is been with a certain area, so how to calculate is simple, by taking an angle which is perpendicular to the area, that is normal to the area. This is the normal, and if we take at this point, this is the normal for this area, the perpendicular for this area, like this is the area and this is the normal, and if we change it, it goes on changing. So this will be the normal. Now this normal to this magnetic field lines is said to be called the angle, that is theta, and we can write it as phi is equals to BA cos theta. Phi is equals to BA cos theta. Next we will see that what will be the angle for 0 degrees and what will be the angle for 90 degrees. That we'll be seeing in the next episode. Thank you for your time. Thank you very much.